Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 17, 2026, about 4 days ago. It presents a framework that allows a humanoid robot to autonomously execute agile parkour, scaling 1.25-meter walls and vaulting obstacles at speeds of 3 meters per second. The paper is titled Perceptive Humanoid Parkour, Training Dynamic Human Skills via Motion Matching. And as we'll see later, the system's ability to chain these skills into long, continuous traversals is really impressive. Well, Figure 1 immediately visualizes these claims with the Unitree G1 robot in action. Panel A displays a high-speed vault at roughly 3 meters per second, and Panel C captures a similar dynamic move over a lower obstacle. Moving to the right, Panel B highlights a vertical challenge, where the robot scales a box 1.25 meters tall. Finally, Panel D depicts a continuous 60-second run, demonstrating how the system chains these skills for long horizon traversal. So, Figure 2 details the framework's pipeline, which unfolds in 4 main stages. Starting on the left, the skill composition module takes atomic human motions and stitches them together using motion matching, creating long, fluid reference trajectories. Next, the teacher training panel shows how these trajectories guide expert policies in simulation, which have access to privileged ground truth data. Then, the student training section distills these experts into a single vision-based policy using a mix of dataset aggregation and reinforcement learning. Finally, the zero-shot sim-to-real panel confirms that this student policy can successfully control the physical robot using only onboard depth sensors. Alright, following the pipeline overview, Table 1 details the success rates across varying speeds and obstacle heights. The columns separate the trials into 1 meter per second and 2 meters per second runs, testing obstacles from 36 up to 76 centimeters. We see that the velocity tracking baseline handles low obstacles easily but fails completely on taller ones, scoring 0%. Conversely, the proposed method in the bottom row dominates the comparison, maintaining over 95% success even on the most challenging 76 centimeter barriers. So, having seen the high success rates, Figure 5 visualizes these behaviors on the physical hardware. Row A captures a high-speed cat vault, where the robot clears an obstacle in under 0.8 seconds. Below that, Row B demonstrates a drop landing from a 1.25-meter wall, proving the system's stability. Finally, Row C tracks a continuous 48-second run. Crucially, notice the human in the yellow vest moving obstacles mid-traversal. The robot perceives these changes and adapts its path in real time. Okay, while Figure 5 showed the final performance, Table 2 now dissects the specific components that make it possible. The top rows test motion matching density, revealing that using only extreme distances or sparse data causes success rates to drop significantly on the 94-centimeter obstacles. The middle section is even more striking because dagger only, which is pure imitation learning, fails almost completely, with scores collapsing to near zero. It is only by combining imitation with reinforcement learning, as shown in the bottom row, that the system achieves consistent success across all conditions. Wrapping up, 2 takeaways stand out. First, motion matching successfully bridges the gap between sparse human data and continuous robotic control. Second, blending reinforcement learning with distillation proves essential for mastering these high dynamic maneuvers where pure imitation falls short. This framework really pushes humanoids from stable walking into the realm of agile, athletic performance. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.